everyone, today I'm going to present a wideband circularly polarized complementary antenna for millimeter wave applications. One method to achieve wide bandwidth in CP antenna design is through the use of complementary antenna. When the electric dipole and main dipole are parallel to each other and in phase excited by the same source, they will naturally have 90-degree phase difference and generate two orthogonal electric fields. Therefore, circular polarization can be generated. Based on this idea, we propose a wideband circularly polarized complementary antenna for millimeter wave applications. Here shows the configuration of the proposed antenna element. It is a two-layer structure. Substrate 1 is the SIW structure with a longitudinal dot edge on the top of the substrate and functions as a fit to excite the radiator. The radiator in substrate 2 consists of a patch dipole and a loop antenna, which are excited differentially by the longitudinal dot edge on the top surface of substrate 1. Here shows the current distribution of the proposed antenna element. It can be seen that the current is rotated in clockwise direction, which indicates that the proposed antenna has a left-hand CP radiation. The simulated impedance bandwidth of the proposed antenna element is about 46%, from 48.47 to 77.46 GHz, and the 3 dB AI bandwidth is about 47.3%, from 51.64 to 83.61 GHz. Here shows the radiation patterns of the proposed antenna element. To further enhance the antenna gain, an A-by-A antenna array is constructed. It should be mentioned that the energy flowing into the radiating elements, colored in red, blue, yellow, and green, are in descending order. It can be seen in this figure that the non-equal power distributed feeding network introduces an average 1.9 dB solid level enhancement, while the AI performance is slightly affected. This is the prototype of the A-by-A antenna array. The simulated impedance bandwidth is about 33.8%, from 56.11 to 78.95 GHz. The 3 dB AI bandwidth is about 38.8%, from 53.57 to 79.32 GHz. The overlap bandwidth is about 34.3%, from 56.11 to 79.32 GHz. These are the radiation patterns of the proposed A-by-A antenna array. So, a novel wideband CP complementary antenna and an A-by-A antenna array have been proposed in this report. It achieves a wide impedance bandwidth and 3 dB AI bandwidth. The merits of this antenna are its simple structure, easy fabrication, and wide bandwidth. For more details, please refer to our paper. Thank you for listening.
We are happy to share our recent research entitled A High-Gain Wideband Circularly Polarized Antenna with Multibeam Radiation for Millimeter Wave Applications. I am Qingyi Guo from Shenzhen University. My presentation is divided into 5 parts. First, I will introduce the background. Circularly polarized antennas are suitable for wireless communications for their capabilities to suppress multipath fading and avoid polarization mismatching. Compared to bulky horn antennas or high-profile lenses, slot antennas and arrays yield advantages such as simple structure, low profile, and ease of fabrication. On the other hand, the high-gain beam scanning antenna can maintain certain coverage ranges while transmitting high-quality signals and has become a popular candidate for telecommunication applications. Hence, we want to develop a millimeter wave ultra-wideband CP slot antenna with high-gain multi-beam radiations. The proposed slot breaks the limit of width of SIW and connect with each other to form a long slot structure. This technique of the proposed design produces a lower Q factor, contributing to wider gain bandwidth. In order to fit the long slot structure, a substrate-integrated parabolic reflector is designed as shown in this figure. The parabolic reflector is designed in a single-layer PCB structure by using metallic vials. It is a 2D structure. From the radiation pattern of it, we can obtain that directive beam can be achieved. The gain enhancement of the long slot is shown in this figure. By adding upper cavities above the long slot structure, nearly 5 dB gain enhancement can be achieved. In order to achieve CP radiation, a modified shaped polarizer is utilized for wideband LP to CP conversion. The shape structure is used to maintain gain values at high frequency points. Finally, by adding the differential fit multi-pot feeding networks, multi-beam radiation can be achieved when different pots are excited individually. Herein, we designed 2 prototypes for validating performance of the whole antenna. The structures of the 2 prototypes are the same except the feeding networks. From the measured results, we can obtain that the operating frequency is from 58 to 94.5 GHz. The matching bandwidth of it is around 48%, with in-band AR below 3 dB. The maximum realized gain measured is around 20.5 dBIC. The maximum in-band gain variation is less than 3 dB. From the simulated and measured radiation pattern, we can obtain that the measured side loop level is around -10 dB. The measured cross polarization level is around -18 dB. The maximum of gain variation in passband is less than 3 dB for antenna operating at beam tilted states. Here is the summary. This article introduces a novel design method to construct a wideband and high-gain CP antenna operating across V and W bands. It operated at 75 GHz with 48% matching bandwidth. Thank you for your attention.
Hello, I'm Zhao. I am from Nanjing University of Science and Technology, and my presentation topic is ultra-wideband and low-profile circularly polarized Waveguide antenna array with wave absorber form wave applications. I will present work in the following 4 areas. First, background. In recent years, there has been a growing demand for wireless transmission technology. Within the realm of 5G communication systems, the utilization of point-to-point links necessitates antennas with high gain and low loss to counter atmospheric attenuation and transmission loss due to the wave wavelengths. For example, military, civilian, communication, and smart park. Needs antenna element analysis. It is clear that the antenna element undergoes a transition from an unnotched state to a notched state. The following figure illustrates the principle of operation of a broadband CP antenna device, where the retained portion of the broadside of the metal wall of the Waveguide can be equated to a dipole structure that provides a current J, which provides a field component parallel to the YOC plane. The open portion of the rectangular Waveguide and the symmetric notch structure excites a localized magnetic current Jm and provides field components parallel to the XOS plane. This provides the antenna device with an ultra-wideband plus 90 degrees or 90 degrees phase difference, which satisfies the phase condition for ultra-wideband CP antennas. Then the right figure shows the simulation results. Then is the antenna array design. When the antenna elements are evenly spaced, a problem arises. 3 transverse notches are formed in the XOS plane. The antenna array will reflect electromagnetic waves in the z-axis direction during operation, affecting the CP performance of the antenna array. The solution is to introduce a wave-absorbing structure at the transverse notches. Structure will absorb the electromagnetic waves diffused into the transverse slots and reduce their reflection. The following figure shows the wave absorber structure under the periodic boundary condition from the reflection coefficient. The combination of type 1 and type 2 can realize full band wave absorption from 18 to 32 GHz. The figure on the right shows the effect of the presence or absence of an absorber structure on the radiation performance of the array, with the main improvement being in the axial ratio. In order to take into account the weight, profile height, and efficiency of the whole array, the feed network designed by SICL is adopted to meet the broadband feeding requirements. This is the processing test of this prototype. The upper sideband, IF, lower sideband directional map, reflection coefficient, axial ratio, and antenna efficiency are in good agreement with the simulation, and the antenna efficiency is in good agreement with the simulation. Last is conclusion. Performance comparison of published circularly polarized array antennas is given in the table. The 4 multiplied by 4 array antenna of this work has wider impedance bandwidth and axial ratio bandwidth, 48%, as well as lower profile height. This method also has the advantage of low design complexity, which reduces the difficulty for the design and fabrication of antenna arrays. Thanks for your attention.